A supernova is one of the most powerful and awe-inspiring events in the universe, marking the explosive death of a massive star. These cataclysmic outbursts release more energy in a few seconds than our Sun will emit in its entire lifetime, briefly outshining entire galaxies. Supernovae play a crucial role in cosmic evolution, dispersing heavy elements into space and seeding the next generation of stars and planets. There are two main types of supernovae, core-collapse and thermonuclear. Core-collapse supernovae occur when a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel. Without the outward pressure of fusion, gravity causes the core to collapse, triggering a violent explosion. The remnant may form a neutron star or, if the core is massive enough, a black hole. Thermonuclear supernovae, on the other hand, happen when a white dwarf in a binary system accumulates too much mass from a companion star. This excess material triggers a runaway nuclear reaction, obliterating the white dwarf in a brilliant flash. Supernovae serve as cosmic factories for elements like iron, nickel, and gold. In fact, the calcium in our bones and the iron in our blood were forged in these stellar explosions billions of years ago. Without supernovae, the universe would lack many of the elements essential for life. Beyond their role in chemical enrichment, supernovae influence galactic dynamics. Their shockwaves trigger the formation of new stars by compressing interstellar gas clouds. Some supernovae leave behind remnants like the Crab Nebula, which continues to expand centuries after the initial explosion, providing astronomers with valuable insights into stellar death and rebirth. These stellar explosions are also crucial cosmic beacons. Type Ia supernovae, for example, have a consistent peak luminosity, making them essential for measuring vast cosmic distances. By studying these standard candles, astronomers have determined that the universe is expanding at an accelerating rate, leading to the discovery of dark energy, a mysterious force driving cosmic expansion. The study of supernovae is not just a matter of astronomical curiosity, it has practical implications for Earth. A supernova occurring within 50 light-years could pose a significant threat to our planet, stripping away the ozone layer and exposing life to lethal radiation. Fortunately, no nearby stars are currently on the verge of such an explosion. Supernovae also produce some of the most exotic objects in the cosmos. A core collapse event can result in the formation of a neutron star, an ultra-dense remnant where a sugar cube-sized piece of material would weigh as much as Mount Everest. Some neutron stars become pulsars, spinning rapidly and emitting beams of electromagnetic radiation. If the collapsing core is massive enough, it forms a black hole, an object with gravity so intense that not even light can escape. The first recorded supernova visible to the naked eye was observed by Chinese astronomers in 185 CE. Since then, historical records have documented several spectacular events, including the famous SN 1054, which created the Crab Nebula, and Kepler's supernova of 1604, which shone brightly for weeks. Today, astronomers use powerful telescopes like Hubble and the Vera C. Rubin Observatory to detect and study these cosmic detonations. Supernovae also generate powerful neutrino bursts, subatomic particles that barely interact with matter. The detection of neutrinos from SN 1987A in the Large Magellanic Cloud confirmed key theories about stellar collapse and provided rare direct observational data on the inner workings of a dying star. Some supernovae challenge our understanding of stellar physics. Hypernovae, for instance, are even more energetic than regular supernovae and may be linked to long-duration gamma-ray bursts, the most intense explosions in the universe. The nature of so-called superluminous supernovae, which shine 10 times brighter than ordinary supernovae, remains an active area of research. Another mystery is the fate of Betelgeuse, a red supergiant in the Orion constellation. This massive star is nearing the end of its life and could explode in the next few thousand years, or even tomorrow. If it does, it will be visible in broad daylight from Earth, offering humanity a front-row seat to one of the most extraordinary cosmic events. Supernovae not only illuminate the past but also shape the future of astrophysics. Scientists are using advanced simulations, high-energy observatories, and gravitational wave detectors to probe the secrets of these stellar cataclysms. Understanding supernovae could help answer fundamental questions about the nature of matter, the origins of elements, and the ultimate fate of the universe. The next nearby supernova could revolutionize our understanding of the cosmos. Telescopes worldwide are constantly scanning the sky, hoping to catch the next great stellar explosion in real time. When it happens, astronomers will be ready. Supernovae are also responsible for some of the most extreme and mysterious phenomena in the universe, including magnetars. Magnetars are highly magnetized neutron stars, with magnetic fields trillions of times stronger than Earth's. These bizarre remnants occasionally release powerful bursts of X-rays and gamma rays, capable of affecting our planet's upper atmosphere even from thousands of light-years away. The origin of magnetars is still debated, but many scientists believe they are born from the most energetic core-collapse supernovae. Another intriguing class of stellar explosions is the so-called failed supernova. In these rare cases, a massive star collapses directly into a black hole without producing a visible explosion. Some astronomers have observed stars that seem to vanish without a trace, hinting that direct collapse black hole formation might be more common than previously thought. If confirmed, this could reshape our understanding of how black holes form and evolve. Supernovae are not only natural laboratories for studying high-energy physics, but they also play a role in shaping entire galaxies. When a supernova explodes, it injects vast amounts of energy into the surrounding interstellar medium. This feedback process can regulate star formation by either compressing gas clouds to trigger new star birth or dispersing gas and preventing further star formation. In extreme cases, multiple supernovae can create superbubbles, vast cavities in galaxies filled with hot, ionized gas. The Milky Way itself has been shaped by countless supernovae over billions of years. Some astronomers suspect that past supernova explosions may have influenced the evolution of life on Earth. The hypothesis of a supernova-induced mass extinction suggests that cosmic rays from a nearby explosion could have altered Earth's atmosphere, leading to climate change or increased mutation rates. While no definitive evidence links a supernova to past extinctions, isotopic traces of iron-60 found in deep-sea sediments suggest that at least one supernova occurred relatively close to Earth within the last few million years. The search for supernovae extends beyond our own galaxy. Astronomers regularly discover and analyze supernovae in distant galaxies, using powerful telescopes like the James Webb Space Telescope. These extragalactic supernovae provide crucial data for understanding the early universe, as they offer glimpses into the lives and deaths of the first generations of stars. Some of the earliest supernovae may have contributed to the reionization of the universe, a period when the first stars and galaxies transformed the cosmos from a dark, neutral state into the bright, structured universe we see today. The interplay between supernovae and cosmic rays is another fascinating area of research. Supernova remnants, like the famous Tycho and Cassiopeia A remnants, are believed to be primary accelerators of cosmic rays, high-energy particles that travel near the speed of light. When these charged particles collide with the interstellar medium, they produce gamma rays, which can be detected by space telescopes. Understanding the origins of cosmic rays could shed light on some of the most energetic processes in the universe. In recent years, astronomers have begun using machine learning and artificial intelligence to detect and classify supernovae more efficiently. Automated surveys like the Zwicky Transient Facility, ZTF, and the upcoming Legacy Survey of Space and Time, LSST, are expected to discover thousands of new supernovae every year. These vast datasets will help refine theoretical models and potentially uncover new, exotic types of stellar explosions that defy current classification. Another breakthrough in supernova studies came with the advent of gravitational wave astronomy. When two neutron stars collide, a process often initiated by a supernova, they produce both a visible explosion, called a kilonova, and gravitational waves, ripples in spacetime first predicted by Einstein. The detection of gravitational waves from the neutron-star merger GW170817 confirmed that kilonovae are responsible for creating heavy elements like gold and platinum, solving a long-standing astrophysical mystery. As technology advances, astronomers hope to capture a supernova in the earliest stages of its explosion, something that has rarely been observed in real time. Supernova early warning systems, which monitor nearby stars for pre-explosion activity, may soon allow scientists to predict and study these stellar deaths as they unfold. If successful, such efforts could provide unprecedented insights into the final moments of massive stars. Even in death, supernovae continue to shape the universe in ways we are only beginning to understand. Their explosive legacies live on in the stars that form from their remnants, in the elements that compose planets and life itself, and in the mysteries they leave for future generations to explore. Supernovae are not just violent endings, they are also cosmic rebirths, setting the stage for the next generation of stars, planets, and even life. The elements forged in these titanic explosions, carbon, oxygen, silicon, iron, and countless others, become the building blocks of everything we see around us. Every atom in our bodies heavier than hydrogen and helium was, at some point, created in the heart of a massive star and released into space by a supernova. In this sense, we are all made of stardust. One of the most enigmatic consequences of supernovae is the creation of exotic objects like quark stars, a hypothetical state of matter even denser than neutron stars. Some physicists speculate that under extreme pressure, neutrons in a collapsed star could break down into their constituent quarks, forming an incredibly compact remnant. While no confirmed quark stars have been observed, ongoing studies of unusually massive neutron stars suggest that these strange objects might exist. Supernovae are also responsible for some of the most luminous transient events in the cosmos. One such phenomenon is the parainstability supernova, a rare explosion that occurs in extremely massive stars, at least 150 times the mass of the Sun. Unlike typical core-collapse supernovae, which leave behind a remnant, parainstability supernovae completely annihilate the star, leaving no black hole or neutron star behind. These colossal explosions were likely more common in the early universe when massive first-generation stars dominated. Another fascinating class of explosions is the so-called zombie or repeating supernova. Some supernovae, like the peculiar IPTF-14 have defied expectations by exploding multiple times over several years instead of fading away. This challenges existing models of stellar death and suggests that some massive stars may undergo prolonged, episodic eruptions before finally collapsing for good. Supernova remnants, though often associated with destruction, can also be sites of intense astrophysical activity. Pulsar wind nebulae, for instance, form when a rapidly spinning neutron star, or pulsar, injects high-energy particles into its surrounding environment. One of the most famous examples is the Crab Nebula, which houses a central pulsar that rotates 30 times per second, emitting beams of radiation that sweep across space like a cosmic lighthouse. The effects of supernovae extend far beyond their immediate surroundings. Some researchers believe that the cosmic rays generated by supernovae may have influenced Earth's climate over geological timescales. The hypothesis, known as the cosmic ray climate connection, suggests that variations in supernova activity in our galactic neighborhood could affect cloud formation and, consequently, global temperatures. If true, this would mean that the history of life on Earth has been subtly shaped by distant stellar explosions. From a technological standpoint, the study of supernovae has led to innovations that extend beyond astrophysics. The techniques developed to detect and analyze supernovae, such as advanced image processing, machine learning, and high-energy particle detection, have applications in medical imaging, nuclear physics, and even materials science. The hunt for neutrinos from supernovae has also inspired the construction of massive underground detectors, which are now used for monitoring nuclear activity and searching for rare particle interactions. Looking forward, astronomers are eagerly anticipating the next nearby supernova, as it would provide an unprecedented opportunity to study these cosmic explosions up close. Some candidates, like Betelgeuse and Eta Carinae, are closely monitored for signs of impending collapse. When the next supernova occurs in the Milky Way, it will not only be a spectacular sight but also a moment of scientific discovery, potentially answering long-standing questions about stellar evolution, nucleosynthesis, and the nature of extreme matter. As we peer deeper into the universe with increasingly sophisticated telescopes, we continue to uncover new mysteries about these celestial explosions. Each supernova, whether a fiery death or a rebirth of cosmic matter, tells a story of transformation, destruction, and creation, a cycle that has shaped the universe for billions of years and will continue to do so for eons to come. Supernovae are also key players in the cosmic web, the vast structure of galaxies, filaments, and voids that define the large-scale architecture of the universe. When a supernova explodes, it not only enriches its host galaxy with heavy elements but also injects immense kinetic energy into the interstellar medium. This energy influences star formation rates and can even drive galactic winds, powerful outflows of gas that regulate a galaxy's growth and evolution. In extreme cases, these winds may strip galaxies of their star-forming material entirely, leading to the eventual death of a galaxy. Some of the most puzzling supernovae are those associated with gamma-ray bursts, GRBs, the most energetic explosions known. Long-duration GRBs are thought to arise from the deaths of particularly massive stars, where the collapsing core forms a rapidly spinning black hole. This process generates twin jets of relativistic plasma that pierce through the dying star, releasing an immense burst of gamma rays detectable across billions of light-years. GRBs are so powerful that a single event can briefly outshine all the stars in its host galaxy combined. Scientists are still unraveling the precise mechanisms behind these extreme events and their role in shaping the universe. Another fascinating phenomenon linked to supernovae is the presence of runaway stars. These are high-velocity stars that have been ejected from their home systems due to a supernova explosion. When a massive star in a binary system explodes, the sudden loss of mass can send its surviving companion hurtling through space at incredible speeds. Some runaway stars are traveling so fast that they may eventually escape the Milky Way entirely, becoming intergalactic wanderers. Supernovae also play a crucial role in one of the biggest mysteries in cosmology, dark energy. Observations of type Ia supernovae in distant galaxies revealed that the universe's expansion is not slowing down due to gravity but is instead accelerating. This groundbreaking discovery, which earned the 2011 Nobel Prize in Physics, suggested the existence of dark energy, an unknown force that makes up roughly 70% of the universe. Without supernovae acting as cosmic mileposts, this revelation about the fundamental nature of the cosmos might never have been made. Even within our own solar system, evidence of past supernovae can be found. Scientists have discovered traces of iron-60, an isotope produced in supernovae, embedded in Earth's deep-sea sediments, on the Moon, and even in Antarctic ice. These findings suggest that one or more nearby supernovae may have occurred within the last few million years, possibly influencing Earth's environment in subtle ways. Some researchers speculate that these explosions may have contributed to evolutionary changes by increasing mutation rates or altering atmospheric chemistry. The future of supernova research is brighter than ever. Upcoming space missions, such as the Nancy Grace Roman Space Telescope, will survey the sky for new supernovae, helping refine our understanding of dark energy and the expansion of the universe. Meanwhile, ground-based observatories like the Extremely Large Telescope, ELT, will allow astronomers to study supernova progenitors in unprecedented detail, potentially identifying stars on the brink of explosion before they go supernova. One of the most ambitious projects in astrophysics today is the effort to detect a supernova in real time from its earliest moments. By monitoring massive stars with space-based observatories and neutrino detectors, scientists hope to catch the very first signals of a supernova, before the explosion even becomes visible. This would allow for an unparalleled observational campaign, capturing every stage of the event as it unfolds. Supernovae are reminders that the universe is dynamic, ever-changing, and interconnected in ways we are only beginning to grasp. From their role in forging the elements that make up planets and life to their influence on the evolution of galaxies and the expansion of the cosmos, these stellar explosions are among the most important and awe-inspiring phenomena in nature. The next supernova could be discovered at any moment, and when it does, it will undoubtedly bring new insights into the workings of the universe. Supernovae are also linked to some of the most extreme astrophysical environments in the universe, including accretion disks around black holes and the violent interactions within dense star clusters. When a supernova occurs in a crowded stellar environment, such as a globular cluster or the core of a galaxy, the energy released can disrupt surrounding stars, trigger new waves of star formation, or even influence the motion of nearby black holes. Some astronomers believe that repeated supernova explosions in the centers of galaxies may play a role in feeding the supermassive black holes that reside there, providing them with the matter needed to grow. Another intriguing connection between supernovae and black holes comes from the study of so-called fallback supernovae. In these cases, the initial explosion is not strong enough to fully eject the star's outer layers, causing some of the material to fall back onto the collapsed core. This process can lead to the formation of a black hole rather than a neutron star and may explain why some black holes appear to be born with unexpectedly high masses. The study of fallback accretion is helping astrophysicists understand the distribution of black hole masses and the conditions under which they form. Beyond individual stars and galaxies, supernovae may also have had profound effects on the early universe itself. During the first few 100 million years after the Big Bang, the universe was filled with primordial hydrogen and helium, with little to no heavier elements. The first generations of supernovae, originating from massive population 3 stars, were responsible for producing the first heavy elements, fundamentally altering the composition of the cosmos. Without these early supernovae, later generations of stars, capable of forming planetary systems and eventually life, would never have been possible. Interestingly, supernovae may also act as natural laboratories for testing the fundamental laws of physics. The extreme conditions inside an exploding star push the boundaries of our understanding of nuclear physics, particle interactions, and even the behavior of gravity under extreme densities. For example, the study of neutrinos from supernovae provides insights into weak nuclear interactions, while observations of supernova remnants offer constraints on alternative theories of gravity that go beyond Einstein's general relativity. One of the most exciting developments in modern astrophysics is the growing capability to study supernovae across multiple wavelengths and messengers. Traditionally, supernovae were studied using visible light, but today, astronomers also observe them in X-rays, gamma rays, radio waves, and even through gravitational waves and neutrinos. This multi-messenger approach allows for a more complete picture of the explosion, revealing details about the supernova structure, the nature of its progenitor star, and the dynamics of the surrounding environment. For example, some supernovae produce powerful radio emissions long after the explosion has faded from visible light. These radio signals provide clues about the interaction between the supernova ejecta and the surrounding interstellar medium. In some cases, they reveal the presence of dense, previously undetected stellar winds or companion stars that shaped the explosion. Similarly, infrared observations are crucial for studying supernovae hidden behind thick clouds of dust, which would otherwise remain invisible to optical telescopes. The role of supernovae in planetary system formation is another area of active research. Some scientists believe that shockwaves from nearby supernovae may have triggered the collapse of the molecular cloud that eventually formed our solar system. Isotopic anomalies in meteorites, particularly the presence of short-lived radioactive isotopes like aluminum-26, suggest that a supernova explosion may have enriched the early solar nebula, influencing the chemical composition of the planets and potentially even playing a role in the conditions that led to life on Earth. Looking even further into the future, some researchers speculate about the eventual fate of supernovae in an aging universe. As star formation slows down over cosmic timescales, the rate of supernovae will decline as well. However, even in a far future universe dominated by long-lived, low-mass stars, some forms of stellar explosions may still occur. White dwarf mergers, for instance, could continue producing Type Ia supernovae for trillions of years, providing one of the last sources of energy and illumination in an increasingly dark and quiet cosmos. Despite all that we have learned, supernovae continue to surprise astronomers with unexpected behaviors and exotic variations. Some stars defy predictions by exploding at lower or higher masses than expected, while others produce unusual light curves that challenge existing models. The discovery of new classes of supernova-like explosions, such as fast blue optical transients, FBOTs, and calcium-rich transients, suggests that our understanding of stellar deaths is still incomplete. Each new supernova observed adds another piece to the puzzle, helping refine our knowledge of how stars live and die. The study of supernovae is not merely an academic pursuit, it has profound implications for our understanding of the universe and our place within it. From the origins of elements to the fate of galaxies, from the mysteries of dark energy to the physics of extreme matter, these stellar explosions hold the keys to some of the biggest questions in science. As new telescopes, detectors, and technologies come online, the next generation of astronomers will continue uncovering the secrets hidden within these cosmic firestorms, ensuring that the story of supernovae is far from over. Supernovae also serve as cosmic time capsules, preserving information about the physical conditions of the universe at different epochs. By studying the remnants of past explosions, astronomers can reconstruct details about the environment in which these stars lived and died. In some cases, supernova remnants contain traces of interactions with dark matter, offering a potential observational window into one of the greatest mysteries in modern physics. One of the most fascinating and poorly understood aspects of supernovae is their potential connection to fast radio bursts, FRBs. These mysterious millisecond-long bursts of radio waves originate from distant galaxies and often appear to be linked to magnetars, which are themselves the remnants of core-collapse supernovae. Some scientists propose that certain FRBs may be caused by highly energetic processes occurring in young, highly magnetized neutron stars. If this connection is confirmed, it would provide another compelling example of how supernovae continue to shape the universe long after their initial explosion. Beyond their immediate astrophysical impact, supernovae have left a lasting imprint on human culture and history. The observation of bright supernovae in the night sky has been recorded in ancient Chinese, Japanese, and Middle Eastern texts. The most famous example is SN 1054, which created the Crab Nebula and was documented by astronomers across multiple civilizations. More recently, the supernova of 1572, observed by Tycho Brahe, helped challenge the prevailing Aristotelian view that the heavens were unchanging, contributing to the scientific revolution. Modern supernova discoveries continue to captivate both scientists and the general public. The advent of citizen science projects, such as the Supernova Hunters Initiative, allows amateur astronomers to participate in the discovery and classification of supernovae. With automated surveys scanning the sky every night, it is now possible for non-professionals to play a role in identifying these cosmic explosions in near real time. The growing importance of artificial intelligence, AI, in supernova research cannot be overstated. Machine learning algorithms are now used to sift through massive amounts of astronomical data, identifying supernova candidates far faster than human observers. These AI-driven techniques allow researchers to detect rare and unusual supernovae that might otherwise be overlooked. In the coming years, AI-powered sky surveys, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to catalog millions of supernovae, providing an unprecedented statistical view of stellar explosions across cosmic history. One of the most pressing open questions in astrophysics is how supernovae influence galactic habitability. While supernovae enrich the cosmos with life-essential elements, they can also pose existential threats to life on planets. If a supernova occurs too close to a planetary system, the resulting radiation and cosmic rays can strip away planetary atmospheres, disrupt biological processes, and potentially lead to mass extinctions. Understanding the frequency and distribution of supernovae helps scientists assess the long-term viability of habitable worlds in the Milky Way and beyond. Despite their destructive potential, supernovae may have also played a role in catalyzing life. Some hypotheses suggest that cosmic rays from supernovae could have influenced the chemistry of early Earth's atmosphere, helping to generate the building blocks of life. Other theories propose that the radiation from a nearby supernova could have driven evolutionary changes by increasing mutation rates, potentially accelerating the development of complex organisms. Looking ahead, future supernova research will likely focus on identifying progenitor stars before they explode. Recent observations suggest that some red supergiants undergo dramatic changes in their final years, such as shedding large amounts of mass or experiencing brief bursts of increased brightness. If astronomers can identify a star on the verge of going supernova, it would allow them to observe the explosion in unprecedented detail, potentially solving lingering questions about the exact mechanisms that trigger stellar collapse. The first-ever detection of a supernova in real time from its pre-explosion phase would mark a groundbreaking achievement in astronomy. Such an event would allow scientists to test predictive models, refine early warning systems, and possibly even observe new, unexpected physics. The combination of high-resolution telescopes, gravitational wave observatories, and deep space neutrino detectors is bringing us closer than ever to achieving this goal. Supernovae are more than just spectacular explosions, they are engines of cosmic transformation. Their impact spans the smallest subatomic interactions to the largest structures in the universe. Each new discovery brings us closer to answering fundamental questions about the origin of elements, the behavior of matter under extreme conditions, and the ultimate fate of the cosmos. The next supernova, whether in our galaxy or a distant one, will add another chapter to this ongoing story, revealing new insights into the life cycle of stars and the ever-evolving tapestry of the universe. Supernovae are not just isolated cosmic events, they are deeply interconnected with the formation and evolution of galaxies on grand scales. The sheer energy released by these stellar explosions can shape the interstellar medium, drive powerful shock waves, and regulate star formation over billions of years. Some of the most dramatic examples of this influence can be seen in starburst galaxies, where an exceptionally high rate of star formation leads to frequent supernovae that, in turn, generate massive outflows of gas and cosmic rays. In some cases, the cumulative effect of many supernovae can lead to the creation of large-scale galactic structures known as superbubbles. These are enormous cavities in the interstellar medium, often spanning hundreds of light-years, where the combined explosions of multiple supernovae have pushed away surrounding gas. Some of these superbubbles act as hotbeds for new star formation, while others may deplete a galaxy of its gas, effectively shutting down future stellar birth. Supernova-driven winds may also play a crucial role in determining whether a galaxy can sustain life-bearing planetary systems. If a galaxy experiences too many supernovae in rapid succession, the intense radiation and cosmic rays could make it difficult for planets to maintain stable atmospheres. On the other hand, too few supernovae would result in a lack of heavy elements necessary for planet formation. Understanding this balance is essential for estimating the number of potentially habitable worlds in the universe. One of the most intriguing ideas emerging from supernova research is the concept of galactic habitable zones. Just as the habitable zone around a star determines where planets can sustain liquid water, the habitable zone within a galaxy is thought to define regions where planetary systems have the best chance of developing life without being sterilized by supernovae. In the Milky Way, our solar system lies in a relatively stable region, safely distant from the galactic center, where frequent supernovae and other high-energy events might be hazardous to life. At a more fundamental level, supernovae continue to challenge our understanding of physics itself. Recent studies suggest that some supernovae may produce exotic particles beyond the standard model, such as axions or sterile neutrinos, which are hypothesized candidates for dark matter. If these particles are ever detected in the remnants of supernovae, it could revolutionize our understanding of the fundamental forces that govern the universe. Another open question in astrophysics is how certain supernovae give rise to kilonovae, explosions that occur when neutron stars merge. These events, first confirmed through the detection of both gravitational waves and electromagnetic radiation from the neutron star merger GW170817, provide strong evidence that neutron star collisions are responsible for producing many of the universe's heaviest elements, including gold, platinum, and uranium. The connection between supernovae, neutron stars, and kilonovae remains an active area of research, with each discovery shedding light on the complex life cycles of stars. The increasing precision of gravitational wave observatories, such as LIGO, Virgo, and CAGRA, is allowing astronomers to probe deeper into the physics of stellar explosions. If a supernova were to occur in the Milky Way today, gravitational wave detectors might be able to pick up signals from the violent core collapse itself, providing an entirely new way to study these cosmic events. This would be a groundbreaking achievement, as it would allow scientists to directly observe how matter behaves under the extreme conditions present during a supernova. Another exciting frontier in supernova research is the study of their role in the cosmic matter cycle. When a star explodes, it sends vast amounts of gas, dust, and metals back into space, where they eventually mix with interstellar clouds. This process enriches future generations of stars and planetary systems with the materials needed for life. Some of the elements ejected by supernovae eventually form new planets, while others drift through the cosmos for billions of years, becoming part of future nebulae, stars, or even intergalactic space. Looking toward the future, upcoming telescopes such as the Extremely Large Telescope (ELT) and the Square Kilometer Array (SKA) will revolutionize our ability to study supernovae in unprecedented detail. These next-generation observatories will allow astronomers to probe the earliest supernovae in the universe, revealing insights into how the first galaxies evolved. They will also help identify the most distant and energetic explosions, potentially uncovering new classes of supernovae that challenge existing theoretical models. Despite centuries of study, supernovae remain one of the most dynamic and enigmatic phenomena in astrophysics. Each new discovery adds to our understanding of the cosmos, revealing the intricate connections between stellar evolution, galaxy formation, and the very fabric of space and time. The next great breakthrough in supernova research could arrive at any moment, perhaps from a nearby explosion that lights up the night sky, or from a faint signal buried deep in astronomical data, waiting to be uncovered. Whatever the future holds, one thing is certain: supernovae will continue to illuminate the universe, both literally and figuratively, for generations to come. Supernovae are also crucial in the study of intergalactic enrichment, the process by which heavy elements produced in stellar explosions escape galaxies and spread into the vast cosmic voids between them. Observations of distant gas clouds have revealed traces of elements like oxygen, carbon, and iron, clear evidence that material ejected by supernovae has traveled far beyond its original galactic home. This process of enrichment influences the chemistry of future galaxies and helps shape the large-scale evolution of the universe. One of the most profound ways in which supernovae influence the cosmos is through their role in regulating the formation of stars. In dense molecular clouds, supernova shock waves can compress gas, triggering gravitational collapse and leading to the birth of new stars. This phenomenon is often observed in star-forming regions such as the Orion Nebula, where shock fronts from past supernovae have left behind intricate patterns of glowing gas and newly formed stellar clusters. In contrast, in some cases, particularly violent supernova-driven winds can sweep away gas from a galaxy entirely, suppressing star formation for millions of years. In dwarf galaxies, which have weaker gravitational holds, supernovae can play an even more dramatic role. A single powerful supernova or a series of explosions in rapid succession can eject a significant fraction of a small galaxy's gas, starving it of the raw material needed to produce new stars. Some scientists suggest that such supernova-driven outflows may explain why many dwarf galaxies contain so few heavy elements compared to their larger counterparts. This mechanism also contributes to the broader understanding of why certain galaxies stop forming stars altogether, a key aspect of galaxy evolution. Beyond shaping galaxies, supernovae may also leave behind long-lasting cosmic footprints in unexpected places. Some researchers have proposed that supernova remnants could be linked to mysterious ultra-high-energy cosmic rays, the most energetic particles observed in nature. These particles, which travel at nearly the speed of light, bombard Earth constantly, yet their origins remain uncertain. If supernova remnants, particularly those involving young neutron stars or magnetars, are confirmed as sources of these extreme cosmic rays, it would provide a major breakthrough in high-energy astrophysics. On a more speculative front, some scientists have even explored the idea that supernovae could be used as natural astrophysical laboratories for testing the behavior of matter under conditions impossible to replicate on Earth. The immense pressures and temperatures inside an exploding star allow for nuclear reactions that go beyond what is possible in human-made particle accelerators. By studying the spectral signatures of elements produced in supernovae, physicists can refine models of nuclear fusion, helping to understand the forces that govern both stellar evolution and the nature of matter itself. Supernovae are also thought to play a role in the evolution of magnetic fields on cosmic scales. The powerful plasma flows generated by supernova explosions can twist and amplify magnetic fields within galaxies, potentially contributing to the large-scale magnetic structures observed in the Milky Way and beyond. Some theories suggest that repeated cycles of star formation, supernova explosions, and gas mixing over billions of years may have helped generate and sustain the magnetic fields that permeate entire galaxies. Another growing area of research is the study of failed supernovae, a rare but fascinating outcome where a massive star collapses into a black hole without producing a visible explosion. In these cases, rather than triggering a brilliant flash, the star simply disappears from view, leaving behind an event horizon from which no light can escape. If scientists can identify more examples of such disappearing stars, it would provide a new window into black hole formation and help constrain the limits of stellar collapse. The continued observation of supernovae across different wavelengths has also revealed surprises about their environments. In some cases, astronomers have detected strong X-ray and radio emissions from supernovae interacting with unexpectedly dense surroundings. These observations suggest that some massive stars undergo intense episodes of mass loss in the years or even months before they explode. This challenges traditional models of stellar death, which assume a more gradual evolution toward the final explosion. With the advent of next-generation space telescopes like the James Webb Space Telescope, JWST, astronomers are now capable of detecting the faint infrared signatures of supernovae in the early universe. This allows researchers to probe some of the very first stellar explosions that occurred after the Big Bang, providing a glimpse into how the first galaxies were enriched with heavy elements. Such studies are crucial for understanding the transition from the primordial universe, composed mostly of hydrogen and helium, to the complex, chemically rich cosmos we see today. In the coming decades, artificial intelligence and machine learning will play an even greater role in supernova research. AI-driven algorithms are already helping astronomers detect and classify supernovae in real time, sifting through vast amounts of sky survey data to identify new explosions as they happen. As technology advances, AI may even be able to predict supernovae before they occur by analyzing subtle changes in the brightness and behavior of massive stars. The potential for discovering entirely new types of stellar explosions remains high. Some theorists have proposed the existence of supernova imposters, events that resemble supernovae in brightness but do not completely destroy the star. These transient events, sometimes linked to massive eruptions in luminous blue variables, LBVs, highlight the diverse and still poorly understood ways in which stars can end their lives. Perhaps most exciting of all is the possibility of witnessing a nearby supernova in our lifetime. If a star like Betelgeuse were to explode, it would become one of the brightest objects in the night sky, visible even during the day. Such an event would provide an unprecedented opportunity for astronomers to study a supernova in exquisite detail, capturing its evolution from the first moments of collapse to the formation of its remnant. Given the unpredictability of stellar death, the next major supernova could happen at any time, in any galaxy, or even in our cosmic backyard. Supernovae remain one of the most powerful forces in the universe, shaping everything from the smallest particles to the grandest cosmic structures. They are the creators of elements, the sculptors of galaxies, and the engines of cosmic evolution. As our observational tools and theoretical models continue to improve, the mysteries of these stellar titans will gradually be unveiled, revealing even deeper connections between the life and death of stars and the unfolding story of the cosmos. Supernovae also hold the potential to reshape our understanding of time, space, and fundamental physics. Some of the most extreme supernovae, particularly those involving the formation of black holes, may generate exotic effects such as time dilation due to intense gravitational fields. Studying these events allows astrophysicists to test Einstein's general relativity in extreme conditions, pushing the boundaries of what we know about the nature of spacetime itself. One particularly fascinating aspect of supernovae is their ability to act as cosmic lighthouses for deep space exploration. The immense brightness of certain supernovae, particularly type Ia, allows astronomers to measure cosmic distances with remarkable accuracy. These standard candles have been instrumental in refining our understanding of the Hubble constant, which describes the expansion rate. However, recent measurements have revealed inconsistencies in the exact value of this constant, leading to the so-called Hubble tension. The discrepancy suggests that there may be unknown physics at play, possibly hinting at new forces or undiscovered properties of dark energy. The connection between supernovae and dark energy remains one of the greatest unsolved mysteries in cosmology. The discovery that the universe's expansion is accelerating, rather than slowing down, was made through careful observations of distant Type Ia supernovae. These measurements revealed that a previously unknown force, now called dark energy, dominates the universe, driving galaxies apart at an ever-increasing rate. Understanding the precise nature of dark energy requires continuous refinement of supernova observations, pushing astronomers to discover ever more distant explosions at the very edges of the observable universe. Supernovae are also central to the search for extraterrestrial life. While their destructive power can be lethal to planets in close proximity, their role in spreading essential elements across galaxies makes them indispensable to the emergence of life. The balance between these two effects, the potential for devastation versus enrichment, plays a key role in determining which parts of the universe are most hospitable to life. Some researchers believe that the periodic occurrence of supernovae in the Milky Way may have influenced Earth's biosphere, triggering evolutionary leaps or even mass extinctions. Recent studies suggest that supernovae may have left signatures in Earth's geological record. For instance, layers of iron-60 isotopes found in ocean sediments indicate that nearby supernovae likely affected Earth's atmosphere within the past few million years. These cosmic events could have altered the planet's climate, increased radiation exposure, or even contributed to minor extinctions. Understanding how frequently such nearby explosions occur, and their potential impact on planetary systems, will help scientists assess the long-term habitability of Earth and exoplanets alike. Another tantalizing avenue of research is the potential role of supernovae in triggering planetary system formation. The shockwaves from supernovae have been observed to compress gas clouds, setting off the collapse that leads to star and planet formation. Some scientists hypothesize that our own solar system may have formed in the aftermath of a nearby supernova. The presence of certain radioactive isotopes in meteorites supports this theory, suggesting that a supernova explosion may have seeded our early solar nebula with the heavy elements that would eventually form the Sun, Earth, and the other planets. From an observational standpoint, astronomers are constantly refining methods for detecting supernovae in the earliest moments of explosion. Recently, several shock breakout events, brief flashes of ultraviolet and X-ray radiation marking the first moments of a supernova, have been detected, providing crucial insights into the structure of dying stars before they explode. Catching these initial bursts in real time remains a major goal of modern astrophysics, as they provide a rare glimpse into the final instance of stellar collapse. Perhaps even more mind-bending is the possibility that some supernovae could produce exotic remnants beyond neutron stars and black holes. Some theorists have speculated about the existence of strange stars, composed of even more fundamental particles called strange quarks. These hypothetical objects would be more compact than neutron stars but not quite black holes, offering a new window into the behavior of matter under extreme pressures. The future of supernova research is incredibly promising. With the upcoming launch of advanced space telescopes and the continued expansion of ground-based surveys, astronomers will soon be able to study these cosmic events in greater detail than ever before. The Vera C. Rubin Observatory's LSST will revolutionize our ability to detect supernovae in near real time, while next-generation gravitational wave detectors may capture signals from core collapse events as they unfold. Combined with increasingly powerful supercomputers capable of simulating these explosions in 3 dimensions, the next decades promise to bring a new era of discoveries in supernova physics. As we continue to probe the universe, supernovae remain among the most important celestial events for understanding everything from stellar evolution to the fate of the cosmos. They are reminders that the universe is in a constant state of transformation, where the death of one star paves the way for the birth of new worlds. Whether they are forging the elements that build planets, shaping galaxies, or revealing the nature of dark energy, supernovae stand as cosmic sentinels of change, lighting the way for future exploration and discovery. Supernovae are among the most powerful and transformative events in the universe. They are both creators and destroyers, forging the elements necessary for life while also unleashing forces capable of reshaping entire galaxies. Their influence extends from the microscopic world of atoms to the vast cosmic structures that define the universe's evolution. From seeding planetary systems with essential materials to serving as beacons for measuring cosmic expansion, these stellar explosions connect the past, present, and future of the cosmos in profound ways. Despite centuries of study, supernovae continue to surprise us. Each new observation brings fresh insights, challenges existing theories, and deepens our understanding of the life cycle of stars. The mysteries surrounding these cataclysmic events, from their role in cosmic evolution to their potential connection with dark energy and extreme physics, ensure that they will remain a central focus of astronomical research for years to come. As our observational tools grow more advanced and our theoretical models more precise, we stand on the brink of a new era in supernova science. The next great explosion, whether in our galaxy or far beyond, may hold the key to answering some of the most profound questions about the universe. Until then, supernovae continue to serve as cosmic milestones, marking the endless cycle of birth, death, and renewal that has shaped the cosmos for billions of years, and will continue to do so for eons to come.